Welcome to Topology Lesson 12. In this lesson, I want to talk about continuous functions in metric spaces. So let's look at a definition for a continuous function in a metric space. We'll see in the following slides there's several equivalent definitions, which we actually prove via theorems, but let's start with this one here. Given two metric spaces, x and y, a function from x to y is continuous at a point x, an element of x, if whenever a sequence converges to x, then the f of that sequence, f of xn, converges to f of x. So let's just repeat that. So whenever you have a function, a sequence in x, the x sub n, that converges to some value small x, then the function evaluated along that sequence needs to also converge to f of x. In other words, that's required in order for a function to be continuous at a point. So implicit in this definition is that the f of x actually exists. If a function from a metric space x to a metric space y is continuous at every x in the metric space, then the function is said to be continuous. And you could also have subsets. So you might have, say, a subset A of x where our function f is continuous, which means it's continuous at every point in A, and it may not be continuous at other points. So that's also possible. We know that from just basic functions and not even calculus, even pre-calculus. So a couple of examples just to ground things here. So hopefully you've seen this type of thing before, and as I say, probably in pre-calculus. So f of x equals x cubed is continuous everywhere. F of z equals z squared is a continuous complex function. We can have discontinuities. Let's maybe draw an example. So let's say we had sorry for the rough example here, but let's say we have a function that's this is minus 3, and then that goes up to, say, I don't know, 1, and then maybe it's 2. The function continues. It's meant to be a straight line. So here you have a function, a real valued function, and it equals minus 3 from minus infinity all the way up to 1, and then at 1 it jumps to 2. So the function's continuous from minus infinity up to but not including 1, and then it's also it's not continuous at 1, and then from just greater than 1, open set, just greater than 1 out to positive infinity, it's continuous again. So the function has just one discontinuity at 1. And the metric spaces here x would be the real valued, the real numbers, and then y would also be the real numbers. So you're just mapping from R to R. So we have a theorem here that gives us effectively an equivalence to our definition of a continuous function at a point. I recopied the definition up here just so we can look at it when we go through the proof. So the theorem is we have two metric spaces, x and y, and we're given that in a function from x to y such that f of x is defined at a point little x. And here's our equivalence here. F is continuous at small x, an element of x, if and only if for each epsilon greater than 0, there exists a delta greater than 0 such that whenever a z, an element of x, satisfies the distance from x to z less than epsilon delta, then the distance between f of x and f of z is less than epsilon. So it's a bit of a mouthful, but let's look at a picture which I've drawn on the bottom of the slide. So what the theorem is saying is f is continuous if for every epsilon greater than 0, so we pick an epsilon greater than 0, then we're able to find a delta such that every delta about point z, x, excuse me, such that every z in the open ball about x, open ball of radius delta, implies that when you take f of z is within epsilon of f of x. So you pick an epsilon, you can find an open ball about x such that all the points in there, whenever you map them via f, you get a value that's within epsilon of f of x. That's the equivalent definition of continuity. So what we're going to do here is this is an if and only if statement. So it's of the form A if and only if B, and what we're going to do is prove the equivalent statement, not A if and only if not B. So we'll let this first part be A and the second part be B, and we'll prove the negation basically. So let's start going in this direction here. In other words, not B implies A. So if this condition doesn't hold, then F is not continuous. So what does it mean to negate this? Well, it means if there exists an epsilon greater than 0, such that for every delta greater than 0, there's some z in x such that the distance between x and z, so in other words, z is in here in this open ball, but f of x, the distance between f of x and f of z is greater than or equal to epsilon. So you're basically not inside the ball anymore. This is out either on the boundary or outside of the ball. I could have just said greater than, but I have greater than or equal to. So the way we use this to prove that the function's not continuous based on this definition here, we've seen this technique, a variation of this technique, where we create a sequence. So let's take, since this says for every delta greater than 0, let's take delta 1 over k and then pick a corresponding z sub k in here such that the distance between x and z sub k is less than 1 over k, but the distance between f of x and f of z sub k is outside of the ball here. So that means we have a sequence, z sub k, that eventually converges on x because we're taking the 1 over k, gets smaller and smaller as k goes out to infinity, but f of z sub k does not converge to f of x. It's always outside of this or on the boundary of this ball. So that contradicts the definition of continuity, which means f is not continuous at our point x. So we've proven if not b, then not a. Now we'll go on the next slide. We're going to prove if not a, then not b. That's much more difficult to understand, so we'll take that slow, but let's do that on the next slide. So we need to prove the theorem going in the opposite direction. In other words, if f is not continuous, then it's not true for every epsilon greater than 0 there exists a delta greater than 0 such that we have this condition here. So in other words, there needs to be some epsilon greater than 0 such that no such delta exists where this condition holds true. That's what we need to prove here, and it's not all that easy, or should I say it's a bit hard to grasp, so we'll try to go through it slowly. So going in the other direction, assume f is not continuous. So I just said that here. So this implies, now we're just working not from the theorem here, but from the definition of continuity. So if f is not continuous at a point x, that means there exists a sequence x sub k such that x sub k converges to x, but f of x sub k does not converge to f of x. And that in turn implies this rather complex statement, which I'll go through here and then I'll explain even further on the next slide. So f of x sub k not converging to f of x implies there's some epsilon sub 0 greater than 0, such that for every natural number, that's what this means here, there exists some number greater than that natural number. So if this natural number, if we pick 100 here, then we're saying there exists some number bigger than 100, 101, whatever, 300, bigger than our chosen n, such that the f evaluated at x sub this index, f evaluated at x sub n, little n sub capital N, and the distance between this and f of x is greater than our epsilon sub 0, and that would break the this argument here, so that we would not have that true. So let's continue. So we'll take our epsilon greater than 0 from this expression, and then we'll just generate, or so to speak, this n sub little n sub capital N for each value of n. This exists, and then we know that the distance between f evaluated x sub n sub capital N and f of x is greater than epsilon sub 0. So we have that for every possible natural number. So we take any delta greater than 0, then we know that there is some n such that the distance between x sub k and x is less than delta. That's just because x sub k converges to x, and this is less than delta for every k greater than n. And so we can just take the associated x sub n sub little n sub capital N, and we know that that's going to be greater than epsilon sub 0 just from our statement up here, where our n sub little n is greater than n. So that violates our condition down here. So we've proven not B. So we have a given epsilon, and there's no delta, such that when your z is less than, distance between x and z is less than delta, that you always have the distance between the f of x and f of z less than epsilon. We've shown that there's always an exception to that for this given epsilon sub 0. Okay, so that's quite a mouthful. It's wasn't all that easy to prove, but the upshot is that we have sort of the old-fashioned, I'll call it the old-fashioned, the calculus type definition is equivalent to the sequence-based definition that we started with at the beginning of this lesson. On this slide, I'm going to go into a little more detail about what it means to negate the definition of a convergent sequence. So first, let's look at what it means to converge in the technical terminology. So a sequence a sub n converges in the limit to some number L means that for every epsilon greater than 0, there exists a capital N in the natural numbers, such that for every small n greater than capital N, we have that the difference, the absolute value, the difference between a sub n and L is less than epsilon. So you just get closer and closer to, your sequence gets closer and closer to L, I should say, as you take bigger and bigger values of n. So how do we negate this? Let's go step by step. So this first statement here, for every epsilon greater than 0, the negation of that is there exists some epsilon greater than 0. So the negation of for every is just one exception. There exists one. And similarly, if there exists an n greater than, just going to this part here, if there exists an n, an element of the natural numbers, the negation would be, instead of just one, there for every n in the natural numbers. And then we have the this statement here. So the original statement is for every n greater than n, we have the implication that the distance between the absolute value of the distance between a sub n and L is less than epsilon. And the negation of this would be there exists some n greater than capital N, greater than or equal to capital N, such that this a sub n minus L is greater than or equal to epsilon. And it just needs to be one here, one such small n. So if we put all this together, taking the negations in each place along the way here, we have that there exists some epsilon greater than 0, such that for every natural number n, there exists an n greater than that natural number, such that a, the sequence a at that n minus L is greater than epsilon. So if you recall that we had something like that in the previous slide, but we were talking, instead of a sub n, we were talking about a sequence of f of x sub k, but same idea. So this is the negation. It was so not so easy to see. It took several steps, and just to be honest, I actually put this question into Chat GPT, and it amazingly it put out this detailed statement. I rewrote it a little bit, but I was quite impressed that an AI could take something like this and give the negation of it. So there you have it. You might want to try it yourself on a different AI application and see if you get something similar. So just to reword things here, in other words, there exists some positive distance, epsilon, such that no matter how far out in the sequence you go, in other words, how big you take your n, there will always be some terms in the sequence that stay at least epsilon away from L. And that's the case here. There's some n bigger than n, such that a sub n minus L is greater than epsilon. Okay, so there we have it. We can restate our theorem 88 in terms of open balls. So I've just repeated the theorem here. No changes to what I stated a couple of slides back, but what I want to do is restate this. So starting from f is continuous, we can write this in terms of open balls. F is continuous at a point x if and only if for each epsilon greater than 0, there exists a delta greater than 0, so that whenever z is an element of the open ball centered at x with radius delta, so that's equivalent to this here, then f of z is an element of the open ball centered at f of x with radius epsilon. That's equivalent to this statement here. And we can get even more precise. The first part is the same, but I want to rewrite these last two terms here this way here. So rather than saying z an element of this open ball then this, what we can just say is that f evaluated at any point in the open ball centered about x of radius delta is going to be a subset of the open ball about f of x with radius epsilon. So that's something we're going to use in the next theorem, but I thought I would just kind of point it out explicitly here before we just use it directly. So we can plug this into this theorem here, and after such that, and we have kind of a simpler expression. We have another equivalent definition of continuity here via a theorem. Given two metric spaces x and y and a function that maps between x and y such that f of x is defined at each point in our metric space X. F is continuous at every x an element of X if and only if F inverse of V is an open subset of X for every open set V of Y. So this is related to the open ball interpretation of our theorem 88, which I've just kind of squeezed in here at the bottom of the slide since we're going to use this in our proof. So it's a if and only if statement as before. We have to go in both directions. So let's assume F is continuous on X. Let V be an open set in Y and take any X an element of F inverse of V, which implies that F of X is an element of V. Since V is open, by assumption, there exists an epsilon greater than 0 such that there's an open ball about f of x of radius epsilon that's contained in V. That's because f of x is an interior point. By the second version of our rewrite, this down here, we have there exists some delta greater than 0 such that f of b of x delta is a subset of the open ball about f of x of radius epsilon. And then from up here we have that it's a subset of V. And if we take the inverse of this and this, we get that the open ball about x of radius delta is a subset of f inverse of V. And since we've chosen x arbitrarily, f inverse of V contains an open ball about has an open ball about each of its points. In other words, f inverse of V is open. So that's proves the theorem going in the forward direction. Let's go in this direction here, the opposite direction. So assume f inverse of V is an open subset of X for every open subset V of Y. Take any X, an element of our metric space X, and any epsilon greater than 0. Since the open ball about f of x of radius epsilon is an open set, right? All open balls are open sets. We proved that earlier. Then the inverse of this is open in X. That's basically our hypothesis here. And since F inverse of the open ball about f of x of radius epsilon is open and contains x, there exists some delta greater than 0 such that the open ball about x of radius delta is a subset of f inverse of the open ball about f of x of radius epsilon. Then we apply f to the function f to both sides of this, and we get that f of the open ball about x of radius delta is a subset of the open ball of f of x about epsilon, which is basically this condition here, and thus f is continuous for every x an element of x, since we chose x arbitrarily up here. We can also define continuity at a point using the open sets. I took this from Wikipedia. So for every neighborhood V of f of x, there is a neighborhood U of x such that f applied to U is a subset of V. It means that we have continuity at this point x here. So if we look at the figure, what this is saying is that we're continuous at x, little x is a point within our metric space capital X. What it's saying is that for every neighborhood V of about our point f of x, there exists a neighborhood U about x such that when you apply f to U, f applied to U is a subset of V. So that's pretty simple. And that's, as I say, that's continuity at a point. What we had in the last slide was continuity across the entire metric space X. So we used the term homeomorphism previously in this series of lessons here, and now we can define it a little bit more precisely. So a function f of x mapping it to y between two metric spaces is a homeomorphism if it has the following properties. F is a bijection, in other words, 1 to 1, every element in x is mapped to one and only one element of y, and for every element of y there is an element of x that gets mapped to it. I just wrote it out here in a little bit more detail. F is continuous, so we need to have these three properties hold, and then the inverse of f is also continuous. So if these three things hold, we have what is called a homeomorphism between x and y. So that means x and y are, very similar. They're topologically equivalent, basically. There is a condition known as uniform continuity, which is stronger than continuity in the sense that if the function is uniformly continuous, then it's also continuous. So let's define that here. We have two metric spaces, x and y, and a function f of x maps to y, and that function is uniformly continuous if for each epsilon greater than 0 there exists a single delta, that's the key thing here, a single delta, such that for all x and z elements of x that satisfy the distance between x and z being less than delta, then the distance between f of x and f of z is less than epsilon. So the key thing is your single delta regardless of x and z. That's not the case for regular continuity. We also have this theorem that concerns uniform continuity. If x and y are metric spaces and x is a compact metric space, then every continuous function f from x to y is uniformly continuous. So we have that, and that's known as the Heine-Cantor theorem. On the next slide, I'll give you an example of a function that's not uniformly continuous. On this slide, we have an example of a function which is not uniformly continuous. Look at the function 1 over x from just past 0, not including 0, and to 1, so between here and including 1. And the problem we run into is that this goes off to infinity as you approach 0. So this means that for small values of x and y, even if the difference between x and y is small, so in other words, if you get very close to 0 and you take two values of x and y that are very close together, the difference between f of x and f of y starts to explode as you get closer and closer to 0. So near 0, the rate of change of f of x becomes so large that there's no single delta that can be chosen to ensure that the difference between the value of the function between the 2 points is less than epsilon for all values of x and y less than 0. So that's the problem is here. Otherwise, the function is continuous on this interval 0 to 1, but it's not uniformly continuous as you approach 0. So this is the last lesson concerning metric spaces, but I have a series of lessons that I'm going to develop on topological spaces. So they're more general than metric spaces, and metric spaces are a special case of a topological space. And that'll start with the next lecture, which I haven't developed yet at the time I'm recording this, but I anticipate having roughly the same number of lectures on topological spaces I had on metric spaces.